Hello. My name is Bradley Ung, and today I'll be going over group assignment number 3, which is covering graphs for Dr. Rizk's data structures class, aka COSC2430 at the University of Houston. All right, so the introduction or like the setup for the scenario is that we're in urban planning form at an amusement park, and we want to help decide whether certain designs are good or bad. And we basically just have to create a graph that has functions that can determine the criteria. And these are the 4 criteria. We're given a design blueprint G, which is basically a graph, an undirected graph, a weighted undirected graph, and we have to evaluate its business potential based on these 4 requirements. So for each attraction, there has to be a path that goes from the attraction to every other attraction. What this criteria is saying is that the graph basically just has to be completely connected, or all the nodes have to be connected to each other, and there can't be a node that's like apart from the rest of the graph. And yeah, so basically for every node in the graph, there has to be a way to get to every other node. And criteria 2 is it has to be traversable, or it doesn't have to be, but we are checking if it can be traversed by going over each walkway just once. So what we're doing is we're going to check if the graph can be traversed by going over each edge just once. And what this is asking us to check for is something called a Eulerian trail. And what that is just like a graph that can be traversed by going over each path just once. And the 4th and last criteria is checking what attractions have the greatest number of neighboring attractions. But there is a restriction for this, and it has to have at least 3 neighboring attractions to pass this. So we're trying to find the attractions with the greatest number of neighboring attractions, and the attractions have to be at least three neighboring attractions in degree to pass the criteria. All right, and these are all the assumptions. Yeah, they're pretty simple. We're starting at vertex 0, and yeah. All right, I'm going to switch to the code now. All right, so since this is a group assignment, I didn't write the every single bit of code, but I did like a third of the code since it's a 3-person group assignment. But I'm going to explain like everyone else's part in the code as well. So to start off, we create our main function, which uses the argument manager. So we had to include argument manager up here, and we have all like the argument manager code, as well as the arguments for the main function that would take the inputs files. So yeah, this stuff is pretty simple. And okay, so we're gonna set up a integer for vertices and get it from the inputs, because okay, here's the layout of the input file. So the number of vertices is on the first line, and each line after that is an edge connecting the first vertex to the second vertex. And the third number is the weight of the edge. So we're making a variable for the number of vertices, and we're getting that from inputs. Next, we're going to be initializing our graph. which is a manually implemented class that we created. So I'm going to be switching from the main to the graph files. So here's the H file for the graph. We have a struct declared to use with a function that would be checking for the fourth criteria that I'll go over later. And here's the actual graph class. So we're gonna, for private variables, we're gonna have a graph matrix, which is basically an adjacency matrix for the graph. The chrono matrix is just chronological order. So we can use, we're going to need to use that when we're doing output for the files, since we have to return for criteria 4, we have to return the edges in the neighbors in chronological rather than sorted order. Or chronological as in the order that we got them from inputs. All right, back to the code. This is a vector for the nodes that are visited, which is used in, I think, the function for the fourth criteria as well. Or third criteria? Yeah, third criteria. This is just a simple Boolean that stores whether or not the graph is connected. And it's connected if, like I said, criteria 1. All nodes have to be connected to every other node. This is just the size of the, or number of vertexes in the graph. And this is a helper function that actually, let me check something. All right. This was a helper function we got rid of. Let me just fix that. Okay, so these are all the private members. And public members, this is the constructor, which takes in like the number of vertices from inputs. This is our we have an insert function, a DFS function, a getter function to check if it's connected, a checker for if it's a Euler trail, and a function that returns the line for criteria 4, and a function for criteria 3. All right, so I'm going to go over the criteria one by one. So we need to evaluate if there's a path that goes from that attraction to every other attraction, which would imply that the graph is connected. To do that, let's see, let me scroll back up. So, actually before that, let me go over how to do the constructor and the insert function. So the constructor is just, we're initializing the variables. We're changing the size of the adjacency matrix and the chronological matrix to the size of, or the number of vertexes, so we can access it with .at instead of having to push back. Same thing for the visited Boolean vector. And over here, we're just populating the vectors. For the visited vector, we're just setting everything to false because we're not going to use that yet. And for the graph matrix, aka adjacency matrix vector, we're setting all the vectors that it contains to the size as well. And we're going to populate all the values with -1 to show that there is not an edge between the two edges, or the two vertexes of that would be indicated by the index. If you're not sure what an adjacency matrix is, I recommend doing like a quick Google search, it isn't too complicated. I think it's a pretty easy concept as far as graphs go. Okay. And the insert function, we're just getting from the input file the first two numbers, which are the two vertexes, so v1, v2, and then the weight, so the weight's the third number. And we're putting it in the adjacency matrix at position v1, v2, and v2, v1 because essentially they're the same thing. Or for undirected adjacency matrix, they're essentially like the same thing, and we can use it later on. And for the chronological matrix, we're also putting it in. We're putting it in the first and second thing, and then we're pushing it back, so we can reference it later in chronological order instead of putting it like in the index of the other vector. All right, so let me see. So for criteria one, we want to check if it's connected. To do that, I created a simple DFS function, depth first search, which starts at the base node of 0, which would be like here, I equals 0, and then it's a recursive function that goes through and it sets what's it? It goes through and sets the visited vector to true whenever it encounters the specified vertex through the depth first search. And okay, it takes one value as input, which would be like through recursion, and it starts at 0 specified over here in the main function. And we want it to start at 0 because the assumption is using vertex 0 as a source node in all cases. So yeah, the depth first search goes through and attempts to search through all possible vertexes that can be accessed, starting from vertex 0, and sets all of them to true that it can access. And the second function is connected. It goes through the vector for visited, and if it encounters even a single false, which would mean that this function did not visit that specific vertex, then it returns false. So that means the graph is not connected. But if it goes through all the visited flags and it doesn't encounter one that is false, then it's going to return true because the graph would be connected. And that would fulfill criteria 1. Okay, so for criteria 2, we want to check if it's possible to traverse the entire area to walk each pathway just once. So this is a Eulerian path, and so all this stuff is like it's a lot of text on the Wikipedia page, but what we really want is the properties. Since we're using an undirected graph, here we're not looking for an Eulerian trail, and we don't care about this thing. What we're looking for is this bullet point right here. It has an Eulerian trail if exactly 0 or 2 vertices have an odd degree being the amount of neighbors, and all the vertices with non-zero degree belong to a single connected component. So and this second part is if it's connected, and we already checked that with the first criteria, so we can kind of ignore this for writing the cases of our function for criteria 2. So we need to check if exactly 0 or 2 vertices have an odd degree, which is a lot more simple than like coding a program to search through the graph or to calculate like each possible path through the graph. And the way I created the function for this is I initialize the variable to the number of vertices that have an odd degree. So I initialize it to 0 since we're just starting out. And then I have a for statement that searches through a nested for that searches through the adjacency matrix. So the outer loop, what it does is it goes through every single vertex, and for every single vertex, it has an integer, the degree. It starts at 0 because we haven't checked if it has any neighbors yet. And then what the second for loop does is it checks the vector for the specified vertex from the outer loop. So if we were at like vertex 0, then this would look through the vector for vertex 0 to check if it has any neighbors. So this if function checks if the value at ij is not -1, which would imply that it is in fact a neighbor, and then it would increase the degree because it has a neighbor. And then after it does all that, it checks like every single entry in the vertex or vector of neighbors. If it checks if the degree for the current vertex is odd, then it increments the number of odd vertexes by 1. And then after it goes through and finishes doing all of this, we return number of odd is exactly 0 or number of odd is exactly 2, which is the property of the Eulerian trail. If exactly 2 or 0 vertices have an odd degree. All right, that's criteria 2 done. And then on to criteria 3. Criteria 3 is just asking the minimum length of cable needed to connect and power all attractions. So what we want to do for here is we want to find the minimum spanning tree, which is the minimum path from the start node that would connect every single node in the tree. So for this, my group member decided to use Prim's algorithm. And Prim's algorithm, let me see. Okay, so how Prim's algorithm works is it continuously tries to find the path of least weight. So it sets starting from the source node that you specify, which would be 0 in our case. So how it works is that we have a array of weights or distances. So these are the distances, like the current distances that we have found so far. The first, like the 0th index would indicate the distance from the starting node to the 0th index. The first index would be indicating the distance between the node with index 1 from the starting node, and so on. So how we code this is basically we have a here. This is where the struct comes in, the primnode struct. It basically contains visited and wait, so we don't have to have two separate arrays for checking if a node is visited and checking if or like what the current wait or distance is. All right, so let's get into this. So primnode is pretty not that bad to implement actually, even though it might like seem a little bit complicated from this page. So what we basically did was we have an integer for the minimum length of the tree so far. So this is like the minimum spanning tree length initially, and then like as we go through this function, we'll like add on to this, and eventually return the completed min length. All right, so we initialize the array of the size of however many vertices are inside our graph. And then we have a for loop that populates every single value in the array with a weight of int max, which is basically infinity as specified here because we haven't checked the distance to that vertex yet. So we're going to consider it infinity, which would make it easier like when we're implementing checking whether or not it's smaller than a certain, like whether distances are smaller than the other in our algorithm. And then we're setting all the visited to false. And then we're setting the source vertex, which would be 0, the distance to that as 0 because the distance from vertex 0 to vertex 0 is 0 since it doesn't have to travel. All right, so here's our for loop that, okay, what it does is it loops through for every single vertex in our graph. And okay, so this integer is current smallest edge, which is initialized to int max to make it easier when comparing. And current vertices, int current vertice is the current vertices that is the small, or the vertice that we find as having the smallest distance or weight. And yeah. So we have a for loop that goes through for every vertex as well. And if so what it does is that it checks whether or not the vertex is visited. So if it's unvisited, if the weight isn't int max, which indicates that it has a distance, and if the weight is less than the current smallest edge, then it sets the current vertex to j, and it sets the current smallest edge to the weight of the current vertex. Okay, and then we want this because we don't want to. We have to traverse to the neighbors of the vertex that we check. And then what this for loop does is it once again goes through, it checks the range of the all the vertices, and then we want it so that if the adjacency matrix at the of the current vertices we're checking at k, which is basically like it's looping through the entire vector of neighbors. So it's this condition checks whether or not the current the current edge we're checking in the neighbor's vector is in fact valid, which would make it not equal to -1, as well as if the adjacency matrix that position we're checking has a smaller weight. If so, then we're gonna set the weight of that in our prim array to the current weight in the matrix. So what this thing basically did is, all right, say, let me see. Okay, what this function basically does is that, give me a second to figure out how I want to word this. All right. So say, okay, let's take 0, 1, and 7 as like an example for this. What this for loop basically does is it checks. So how prims work is that we have it checks this node and then it's in the vector of weights or the array of weights or distances we have. It sets the distance to vector 1 as 4 and the distance to vector 7 as 8. And let's pretend this 11 is actually a 1 instead for the purpose of this example. And then since the edge from 0 to 1 is smaller than the edge from 0 to 7, then it decides 1 is like the next vertex we're checking. And then 1 has two neighbors, 7 and 2. If this was a weight of 1 instead, then it would replace the current weight of 8 we have as the new shortest in the weight matrix. So this 8 would be overridden by 1 because it can access it in a total of 5 from 0 to 1, which was 4, and 1 to 7, which is 5. As opposed to 0 directly to 7, which would be 8. So this would be like the new minimum distance to 7, and so on and so on. And then, yeah, after it does all that, it adds on to the minimum length the distance that the current vertex has from the source node, and then it sets the visited to true. And by the end of this this whole for loop stuff, all the vertices are going to be visited. So initially they start out as all unvisited, and then by the time this is done, they're all going to be visited. And the min length is going to be the length of the minimum spanning tree, because it keeps adding on like the minimum weights. And then it just returns the min length, and that satisfies criteria 3. All right, let me go on to criteria 4. So we're just checking for all the attractions that have the greatest number of neighboring attractions, but they also have to have a minimum of 3 attractions. So we're basically just finding the attraction or attractions that have the greatest number of neighbors that also satisfy at least 3 neighbors. All right, and we decided just to return, instead of like a vector or anything, we just decided to return this as a string to make it simpler for the person writing the main function. So let me walk you guys through this. So we're going to initialize a vector of an int vectors called attractions, which would store like all the attractions that that we check and satisfy the conditions. All right, so we have a for loop over here that checks that loops through every single vertex, and then for every single vertex we have another int vector, current attraction, and current attraction it just it pushes back the starting at whatever vertex we're on. And then, and it does this because to make it like simpler when we're converting to a string. So, yeah, the attraction gets the current attraction is it's going to be formatted like, let me see. So, number of or vertex number, and then neighbor 1, neighbor 2, and so on. However, like whatever the neighbors are. All right, and it's going to push back the current vector or the vertex number first to format it like how we want it to. All right, and this if statement checks if the chronological matrix at the current vertex we're checking is greater than or equal to 3, which basically checks if this at least 3 neighboring attractions part of the criteria. And if it does, then it will go through and push back the all the neighbors. That's yeah. So this for loop just pushes back all the neighbors into the current attraction vector, which would be over here. And then this is if the size is greater than or equal to 4, then which would indicate that it has, if the current attractions is greater than or equal to 4, which would mean that it has a vertex number and then at least 3 neighbors, then it would push it back to the number of valid attractions. All right, let me see. Let me just check. All right. All right. And then the next part of this function is, okay, so after this stuff, we're done checking like all the max attraction vertices. And then this next part, we're just converting it all into a string. So we're just initializing an empty string, and then we're adding on like the right formatting as specified in the output file. Yeah, it's nothing too complicated. It just adds like all the attractions, recurses or loops through all the values in the vectors and so on. And then let's see. And then the other case we have is that it has let me see. It doesn't show here. But the other case is that if it doesn't have any neighbors, or if it doesn't have like any vertices with neighbors that are greater than 3, then it's going to return none. So that would be indicated by like a blank result, since the this loops through this like all the elements in the attractions vector, and if the attractions vector is empty, then it'll leave the result string as blank. So we can set the result string to none, and then we return the results. And yeah, that's the fourth function. And then back to the main. And this is basically just how our group member programmed the main. It's just checking like each condition using the functions in the class. So like is connected, is Euler trail, and then formatting it in the right way for the outputs. And then, yeah, and then like it changes like the rating as it goes on, and then it appends the rating to the out. So this would be the rating good. And yeah, that's basically a walkthrough of how my group did GA3. Is there anything else I could go over? Let me just check. All right. Just check if I have to cover anything else. All right. I think that's it.